In all the world today, there is no other railroad classification yard like West Colton. Located on Southern Pacific's main line, 50 miles east of Los Angeles at the Palmdale-Colton cutoff, West Colton covers 560 acres, is 6 miles long and 2,000 feet wide. Its nearly 100 miles of track are laid out on an east-west axis. A tangent yard with running tracks on all sides for greater efficiency. West Colton performs the same function as most other modern classification yards. It takes cars from many areas, sorts them out, and makes them into new trains with other shipments having the same destination. How it does this is the difference between West Colton and every other classification yard in the world. It begins here, in the receiving yard, with 8 tracks that can handle up to 1,800 cars. Crossovers between the 10,000-foot tracks make it easy to yard either long or short trains. The 5 entrances to the receiving yard assure that there will be no interference between incoming trains and the cresting operation. And paved roadways between the wide center tracks permit the use of motorized vehicles for car inspection and servicing. Fully equipped service vehicles make it possible to repair most non-heavy defects right in the receiving yard. This drastically reduces the number of cars going to the RIP track and gets them into outbound trains with a minimum of delay. In the classification bowl, there are 48 tracks with room for 2,800 cars. The tracks are laid out in 2 groups of 24 in the shape of a giant key. In each of the keys, the 4 center tracks have been extended to make 8 departure tracks that speed the handling of up to 180 cars each. Up to 4 trim engines can pull cars in this area without interference. This keeps cars moving out steadily and prevents backups, a major problem in a conventional classification yard. In addition to the 8 normal departure tracks, there are 6 supplemental tracks from which trains can depart. Altogether, there are 14 departure tracks with room for 2,000 cars. On the south side of the yard, a mechanical area contains facilities for servicing cars, locomotives, and cabooses. Incoming bad order cars are sent to the one-spot repair facility for repairs which cannot be made in the receiving yard. Here, facilities are available for heavy maintenance with emphasis on speed to keep cars moving freight. Those cars requiring upgrading or cleaning are sent to the upgrading area. All empty cars leaving West Colton will be clean and in A1 mechanical condition, ready for loading. All inbound locomotives are routed immediately to the diesel facility, a modern version of the old roundhouse, where the first order of business is a wash, followed by spot cleaning and drip drying. While the clear rinse water is recycled for use a second time in the wash, wastewater is cleaned of free oil and sludge before being emptied into disposal lines to be carried away. Just one example of the efforts being made to protect the environment. The diesel facility can accommodate 6 SD-45 locomotives on each of the 3 service tracks, with fuel, lubricating oil, and water nearby. Dry sand for the locomotives is stored in a tower alongside the diesel service facility, while a traveling hopper is used to service any locomotive on any track. But West Colton didn't just happen. Unlike many classification yards of the past, which were located and grew as a matter of expediency rather than plan or logic, West Colton was planned from the beginning to be the most advanced installation of its kind in the world today. It was to embody new concepts for mechanical functions, clerical functions, signal engineering, information systems, management philosophy, and concern for the environment. Before the first scoop of dirt was moved, there were detailed, innovative plans covering everything from the physical layout of the yard to the most advanced railroad information system in the history of modern railroading. The construction of the yard itself was a model of engineering efficiency, which utilized countless time and money-saving techniques. For example, this unique machine placed ties at proper intervals along the prepared roadbed automatically. An onboard crane supplied ties from a flatbed truck as needed so that the operation could continue without interruption. Ties were arranged on an endless chain conveyor, which moved them to the ejecting mechanism and onto the roadbed. With few exceptions, the nearly 100 miles of track in the yard was laid with welded rail. Portable equipment was brought in to produce the strings of rail, some of which were as much as a mile in length. In the classification bowl, the welded rail was pushed from the welding plant directly to the track on which it was to be laid, with rollers to keep it moving. With one track laid, another device was brought into play to guide the next rail to where it was needed. When the rail reached its limit, it was cut, lined over onto the tie plates, and spiked. The operation continued both day and night with a continuous ribbon of rail being pushed out of the welder. With more than 300 switches in the yard, it was decided to prefabricate them at a central location where all hardware could be stored nearby. A template was set up to simplify the placing of the components so that a standard switch could be turned out in a minimum of time. When the switch was completed, a special carrier moved it intact to the spot where it was to be installed and placed it on the roadbed. Recycled blast furnace slag, a waste product from a nearby steel mill, was used for sub-ballast on the roadbed, followed by a layer of finer open hearth slag. The track was then raised and the ties tamped. The track was aligned. Rail anchors were applied, and the footings were dressed with a cover of steel sand. Many other construction operations were carried on simultaneously throughout the yard to ensure its completion on schedule. From the beginning, the primary objective of the West Colton operation has been greater efficiency, the kind of efficiency that would mean better service to Southern Pacific's customers and a greater return on investment for Southern Pacific stockholders. While a conventional classification yard can crest cars at a rate of 3 or 4 a minute, West Colton was planned to classify them at a sustained average rate of 6 to 8 cars per minute. A cresting rate designed to handle even peak loads without backup. To achieve this unbelievably high cresting rate, Southern Pacific, working with the Stanford Research Institute, developed a unique system to permit doubling the normal cresting rate while assuring that cars are well spaced and that coupling speeds do not exceed a safe 4 miles per hour. A conventional retarder yard utilizes a master retarder on the downhill side of the crest, with group retarders at the point where the cars enter the group tracks. The master retarder allows some control and spacing, while the group retarders slow the cars to a safe 4 mile per hour coupling speed. Any attempt to speed up the cresting operation will result in catch-ups at the group retarders. It is possible to prevent catch-ups by increasing the exit speed at the group retarders. This, however, may result in overspeed coupling and possible damage to lading. Prior to West Colton, the only solution was to slow the entire cresting operation to 3 or 4 cars per minute to prevent catch-ups and avoid overspeed coupling. In modern railroading, this is impractical and costly, especially at times of peak traffic. and has led to the widely held belief that the gravity retarder classification yard was becoming obsolete. Southern Pacific solved the problem with a totally new concept of retarder application, utilizing computer-controlled master, intermediate, and group retarders for proper car spacing, and adding tangent point retarders on each of the classification tracks to control coupling speed. Now, cars can be crested at a rate of 6 to 8 per minute, depending on their spread. With a grade of 6% off the crest, the cars attain a speed of approximately 13 miles per hour, with spacing controlled by the master, intermediate, and group retarders. Cars leave the group retarders at just over 9 miles per hour. They exit the tangent point retarders at a speed that is computer calculated to allow a safe coupling speed of approximately 4 miles per hour anywhere on the track. But a cresting operation such as the one at West Colton would not be possible without an equally innovative data system. A data system to weigh cars, measure speed, determine rolling resistance, activate retarders, and align switches. A data system to make cars into blocks and blocks into trains and speed them on to their destination. The data system for West Colton begins at 1 Market Street in San Francisco, home of the Southern Pacific Transportation Company, and the Total Operations Processing System, the TOPS computer. Southern Pacific led the industry in developing its TOPS data system, a complete data network covering car and train activity that supports all aspects of the company's operations. While TOPS is concerned with the operation of the entire line, it furnishes specific data direct to the nearby Terminal Control Computer, the TCC. The Terminal Control Computer is a complete management information system which handles inventory, planning, and various operating displays. While the Terminal Control Computer is located in San Francisco, it communicates with West Colton by means of a high-speed data link over the company's own microwave system. For all practical purposes, the Terminal Control Computer functions as if it were physically located in the administration building at West Colton, alongside the CREST Control Computer. The CCC is strictly a process control system with no functions other than switching and retarding cars. The CCC is made up of 2 separate computers, one online and operating, while the other is in a hot standby mode. Banks of electronic equipment serve to interface the computer with the thousands of sensors, switches, and signal devices in the yard, while a maintainer's console permits manual operation of all computer-controlled functions for maintenance and checkout. Both the CREST Control Computer and the communication system, including microwave and telephones, have backup power to keep them in operation long enough for an orderly shutdown in case of power failure. The operating tower on the top floor of the administration building is the command center from which all cresting operations are controlled. The classification operation begins with the crest yardmaster and the inbound lineup display, which tells him the size and estimated time of arrival of the nearest trains from each direction. His working tube enables him to route all inbound trains to designated tracks in the receiving yard and advise all concerned by means of the computer system without the need for written instructions, phone calls, or other verbal communications. As an inbound train approaches West Colton, the tower man aligns the switches and activates the signals to bring it from the main line into the yard, where the switch tender takes over to safely move the train to its assigned track in the receiving yard. When the train enters the receiving yard, an arrival sensor notifies TOPS and the terminal computer, which then updates all displays to show that the train has arrived and where it is located. After the engine has been removed from the train, the electric blue flag system is activated to protect the mechanical forces who will inspect and service the cars. To accomplish this, the lead carman asks the switch tender for blue flag authorization. The switch tender first aligns all switches away from the track to be protected, then pushes his authorization button, which allows the lead carman to apply electric blue flag protection through a button on his panel. While this is being done, the clerical department is working the inbound waybills so that the inventory can be established in the computer. If the car inspector finds a car that cannot be repaired by the crew in the receiving yard, or one that must go to the upgrading tracks, he reports it to the lead carman so that the car will be crested to the one-spot facility or an upgrading track in the service area. When the receiving yard display tells the yardmaster that both clerical and mechanical have completed their work and the blue flag is off the track, he can start the cresting operation. Using the car movement instruction generator, the CMake format, he instructs the computer to send a message to the engine foreman instructing him to crest the cars on crest list 103. When the data system has provided the crest control computer with the information necessary to classify the cars, it will signal the engine foreman that the next crest list is ready to hump. He can then call up the list give the train engineer a hump signal, and the system will automatically indicate the speed at which the train is to approach the crest. Along the way, approach retarders act as safety measures on the downgrade to the crest. And a weigh-in motion scale weighs each car and determines if it is overloaded and if there is any weight imbalance caused by a load shift. A computer-activated indicator light advises the pin puller if his next cut is 1 or 2 cars or a car that is not to be crested. When the pin is pulled and the car uncoupled, gravity moves it quickly down the 6% slope. Radar checks its speed, and the computer determines the degree of rolling resistance. As each car leaves the master retarder, it is moving at a speed slightly over 13 miles per hour. At each switch along the route, the computer aligns the track to direct the car to its proper place in the classification bowl. Next, the car encounters the intermediate retarder, where its speed is adjusted to maintain proper spacing with other cars. At the group retarder, the computer reduces the car's speed to approximately 11 miles per hour. Finally, the car reaches its assigned track in the classification bowl and passes through the tangent point retarder. When it leaves the tangent point retarder, it is traveling at a speed that will permit it to roll down the track and couple with the next car at a safe coupling speed. With cars being crested at a rate of 6 to 8 per minute, all shipments, both high or low priority, can move through the yard with equal speed and dispatch. The classification list in the crest control computer assigns cars to a primary track according to their destination. If the primary track is full, or if it has reached the prescribed limit in length or tonnage, the computer will swing the cars to the alternate track if one has been assigned. In any event, there is a slough track to take care of overflow, improperly identified cars, or those for which no alternate has been assigned. Overweight cars or those with unbalanced loads are directed by the computer to an overweight track for further inspection. Cars in need of heavy repair are directed to the bad order tracks in the service area. Empty cars that require upgrading for movement of other commodities are sent to the upgrading tracks. Finally, the caboose is crested and routed to the caboose track where it is serviced for its next trip. And the engine foreman pushes the end of list button to clear the system for the next cresting operation. As soon as the crest control computer has the new crest list, the working classification table, and the east car initial and number, it will signal ready to hump, and the sequence will begin again. With a sustained cresting rate of over 6 cars per minute, extra capacity has been engineered into computer-controlled West Colton Yard to enable it to take care of traffic surges without yard backups. And it was planned and built with room for expansion in both the physical facilities and the data system. But a fast cresting operation means nothing unless cars can be moved through the classification bowl onto assigned trains fast and efficiently. The orderly departure of cars is the job of the planners who must get the right car on the right train at the right time. In the near future, West Colton will inaugurate a fully computerized planning system which will utilize real-time inventory and the train's due file of the data system to assign cars to blocks and blocks to trains and issue the necessary crest and trim instructions automatically. From these instructions, the trim yard master is able to call for specific cars to be pulled from the classification tracks and made into blocks and trains quickly and efficiently. The trim yard master utilizes a computer format, an electronic form, on which he indicates the cars, tracks, trains, and other pertinent instructions by entering a number or letter in the appropriate column. From this, the computer's car movement instruction generator, CMIG, types out a message in plain English which instructs the engine foreman in specific detail what cars are to be pulled, where they are located, and what disposition is to be made of them. Once the instructions have been carried out, the engine foreman notifies the trim yard master, who then okays his original message into the computer to update the inventory. The West Colton data system knows the specific location of every car on every track at every moment, no matter how often it may be moved. This helps assure that every car will be handled in a fast and efficient manner. Blocks of cars are assembled according to their destination, with each train carrying one or more blocks. When the complete train has been assembled and the air hose is coupled, ground air is applied at each end. This enables the lead carman in the trim tower to remotely charge the train and make required brake and leakage air test. All that is required of the mechanical crew is to check the piston travel on the cars. When all crew members are aboard and the train is ready for departure, the switch tender aligns the track and gives the engineer his movement indicator light to take him out of the departure yard. As the locomotive passes over the departure sensor, the train is dropped from the West Colton inventory and returned to tops by the terminal control computer. And the tower man routes it onto the main line and passes control to the dispatcher. At West Colton, new ideas are being blended with experience and applied to the solution of problems with the goal of increasing the efficiency of terminal operations and providing better service to the shipper. While West Colton is like no other classification yard in the world, the true test of its worth is in its potential, in what it can contribute to the overall operating efficiency of the railroad. And that, briefly, is the story of West Colton. How it came to be, how it works, and what it can do to increase efficiency and improve service. More than just a modern facility with a unique data system, West Colton is people. People with imagination, people with innovative ideas, geared to the nature and needs of railroading and backed by a progressive management. Only a classification yard that utilizes the best of today's technology can fulfill the needs of modern railroading. West Colton is that kind of yard. It represents a breakthrough in operations for the Southern Pacific that is writing a new chapter in railroad history.